Phani Motamarri is with Department of Computational and Data Sciences at the Indian Institute of Science. He received his PhD from Department of Mechanical Engineering at the University of Michigan, Ann Arbor. His thesis topic is really interesting. It was at the intersection of computational material physics and scientific computing. His main interests of research are developing mathematical techniques and HPI/AI-centric computational algorithms. Okay, that's a brief thing. So he will explain more about that in his talk. He's one of the lead developers of DFT-FE, an open source code for massively parallel DFT calculations that got nominated as a finalist for the 2019 ACM Gordon Bell Prize. This is a prestigious prize for the scientific computing. He is also recipient of SCRB Early Career Research Grant and NSM Exascale for R&D Grant Awards in India. He's going to speak on massively parallel finite element based density-functional theory calculations on hybrid CPU-GPU architectures for large-scale quantum modeling of materials. Over to you, Phani.
Thank you, Professor Datti, for your kind introduction. Should I keep my video on, or is it?
Yeah.
Okay.
Yeah. Yeah.
So I would like to thank again the conference.
People can see you.
Yes. Yeah, I would like to thank the conference organizers, Professor Praveen and Professor Venki Krishnan, for giving me this wonderful opportunity to speak in this conference organized in the memory of late Professor Vasudev Murthy. In fact, before I start my talk, maybe I want to speak a few words about how my association with Professor Vasudev Murthy started. So my association with Professor Vasudev Murthy was actually in the year 2004-2005 when I was an undergrad BTech student. And this was when I worked with Professor Vasu and actually Professor Ravi from the Center for Atmospheric and Oceanic Sciences at IISc as an Indian Academy of Sciences student fellow when I was doing my third year undergrad in NIT Surathkal. So in fact, this work resulted in the form of a publication in DCDS-B, Discrete Continuous and Dynamical Systems B, which was published in the year 2006, I remember. And in fact, through this project, Professor Vasu opened my eyes to the world of scientific research. And I'm deeply indebted to him for that, which played a very crucial role in me choosing an academic career. So with this, I would actually get into my topic of discussion today, which is about massively parallel. Am I audible? Is everything fine?
Yeah, everything. Yeah.
Okay. So yeah, today I will be talking about the work which was partly done at University of Michigan when I was a research faculty member at University of Michigan, and also after I started my stint at the Department of Computational Data Sciences at IISc Bangalore. So this would be on massively parallel finite element based DFT calculations. I would tell you what are those, what is actually DFT briefly, on hybrid CPU-GPU architectures, specifically targeted at large-scale quantum modeling of materials, and what can you do with this. So if you look at quantum modeling of materials, and the quantum mechanical calculations, in fact, have played a very crucial role in determining various properties of materials, be it mechanical properties like elastic constants, equation of state, or for instance, if you want to understand phase stability in materials or transport coefficients, or thermal properties like thermal conductivities, and electronic properties, magnetic properties, the list goes on. This quantum mechanical calculations have played a very important role in actually determining most of these properties. And quantum calculations today, if you notice, it actually accounts for 30% of the world's computational resources today, which means they are very important in terms of its impact which it creates on science. And if you also look at the publications per year, when this quantum material modeling, per year, which was merely 77 in the year 1985. In fact, this is an old data. In 2018, it actually, we can see the number of publications in this area today are actually 18,000. And I think today is like 2022, which might be crossing like 50,000 publications per year. And workhorse for most of these calculations is quantum mechanical theories and density functional theory and post-DFT based techniques, which are some kind of approximations to the original many-body Schrodinger equation. And if you look at these calculations, the impact these calculations had on science today, and 12 of the most cited papers today in scientific literature pertain to quantum modeling of materials. And this had impacted areas ranging from condensed matter, nanotechnology, electronics, organic chemistry, energy materials, spectroscopy, applied physics, you name an area, these quantum modeling of materials actually had significant impact in determining material properties in wide variety of properties, in fact. And today, if you look at the codes which can do this quantum modeling of materials, primarily are based on something called density functional theory. Density functional theory, for which Ohenberg, Walter Kohn, and Sham has received the Nobel Prize in the year 1996, I remember, for their seminal work on this density functional theory, which is some kind of reducing a many-body interacting problem into a non-interacting problem. They provide a prescription which is computationally feasible to compute ground state material properties from which many other things can be extrapolated and can actually be validated with experiments. And then people started, in fact, even before the Nobel Prize was awarded, this particular theory was actually proposed in the year 1964. And from 1980, when the computational resources of computing power started growing, there are 100 available quantum material modeling codes which actually have been developed since the year 1980. And you can see here the number, and these different colors indicates the popularly used codes out there today from 1995 to this year 2020. And there have been exponentially increased the number of citations which actually use these widely available codes out today to do this quantum mechanical calculations of material modeling. But to summarize the state-of-the-art codes, today, which are widely used for this quantum modeling of materials, it can be summarized in this particular cartoon here. So if you look at other areas like combustion modeling, climate simulations, and so on, they can actually leverage these high performance computing architectures to really do large scale calculations. But if you look at these quantum modeling of materials, you need to actually, in order to use this large scale supercomputing resources available today, people just do these high throughput calculations and then kind of try to fill up the massively parallel supercomputer. Really, they're not advances today which are actually happening in the high performance computing community, where you have massive increase in compute power, which actually should be leveraged, and the algorithms should take part. The algorithms you develop must actually be on par with the changes which are happening in the high performance computing architectures today. The reason is, as you see, as I already told you, that the compute power actually is increasing year by year. And today we are also having this heterogeneous architectures, which actually have not only just CPU cores, but also accelerators like GPU, which can actually provide you additional compute if you can leverage the capability of these heterogeneous architectures. If you design your algorithms which can leverage those capabilities. For instance, here, if you today, if you look at in India, so we have this Paramsiddhi AI, which is at the CDAC Pune, which actually has a theoretical peak of 5.3 petaflops, and which is ranked 1 in India and ranked 89 in the world. And we have at IISc, which is Param Pravega, which is a 3.3 petaflops, which essentially means you have large scale supercomputing power even in India, which you can leverage. And if you look at the world, today we have a largest supercomputer, which is in Japan, which is Fugaku, which is around 415 petaflops, and this is ranked 1 in the world. And the Summit had actually 200 petaflops, released in 2018, ranked 2 in the world. And now we are also talking today, in the year 2022, we're going to get the first world's exascale supercomputer, which is basically 10^18 flops. So we are going from this petascale to exascale era, which essentially means the compute power is actually increasing. And are your algorithms taking advantage of these increase in compute power and the kind of massively parallel computing architectures you have today in all domains? maybe in other domains, yes, they are, but in the regime of quantum modeling of materials, they are really not taking advantage of these latest developments in the compute architectures. The key issues for this is, of course, lack of scalable computational methods which can leverage these architectures. Second, not just computational methods, but also the versatile basis sets which actually want to employ in doing these calculations so that you can handle complexities in material modeling at quantum scale. And further, another challenge which comes about in quantum modeling of materials is that you have cubic scaling. These methods scale cubically with number of atoms, which means the computational cost grows cubically with number of atoms. And in some cases, depending upon the method you want to use to do this quantum modeling of materials, it can also be quartic scaling with number of atoms. So this is a huge computational complexity you are actually incurring if you increase the size of the system. So any amount of inefficiencies or any amount of the non-versatile computational methods which you're employing to solve this computation, solve these calculations, in fact, will simply increase the computational cost of these calculations as you increase the number of atoms, and really large-scale calculations are not possible. So, but if you address these key issues where you develop these computational methods which can take advantage of these large-scale supercomputing architectures, where you can actually do real large-scale quantum calculations for material modeling, is there a necessity for those things in the real applications? Yes, there are many material properties which actually need these kind of versatile computational methods and scalable computational methods which can take advantage of these powerful supercomputers today. For instance, here, if you want to understand chemical properties of nanoparticles, like these nanoparticles have their behavior different from the bulk counterparts because their coordination number is different, and the property, the catalytic properties of these cleaved nanoparticles depend upon the surface you're cleaving, and they play a very important role in accelerating or decelerating kind of chemical reactions. And let's say if you want to understand the effect of a large-scale organic molecule, here I'm showing a DNA molecule in the presence of an electrode. You want to understand the electronic structure of these DNA molecule in the presence of electrodes. If you want to design a better nanoscale semiconductor, you actually require the capability of being able to simulate the large-scale atoms in the in these kind of material systems which are placed in between electrodes. And for example, if you also want to understand defects in materials, these defects in materials usually present in very small concentrations, but they can actually have profound influence on the macroscopic properties of materials. And these defects in materials, if you want to understand, because they are occurring in small concentrations, you cannot afford to have very small cell sizes or simulation domains. You actually need to have large scale calculations again to basically try to realistically simulate these defects in materials and understand the influence of these defects on macroscopic properties of materials. So this is kind of the motivation. We really require versatile computation methods, scalable computation methods, and which can reduce the prefactor associated with the computational complexity and address the key issues which I actually mentioned before. So we try to address these particular issues by resorting to real space methods, which is in departure to the conventional plane based. Hello? Is there an issue?
Someone has not
muted. Okay.
Yeah, not muted. Okay.
Okay. Yeah. So, so as I was telling, so we address these issues by resorting to real space methods, which is a departure from the conventional plane-based approaches, which actually use Fourier basis as its basis representations, which actually suffer from many disadvantages, that they restrict the simulation domains to periodic domains, and they actually these basis functions, which conventionally people use this Fourier basis, are non-local in real space, and hence you incur huge communication costs when you actually do these fast Fourier transforms. So, but people traditionally use these basis sets because people actually are interested in understanding periodic properties of materials. But as I said, there are many applications which I actually mentioned, which actually require a departure from the conventional state-of-the-art codes today people are using. So here I'm going to present a real space formulation, which is amenable for discretization with finite element methods, and how the implementations, the real space formulation and the implementation methodology we develop actually push the state of the art in these calculations to actually accomplish many large scale quantum calculation is what I'm going to focus on today. So as I said, Kohn-Sham density functional theory is an approach which actually reduces the interacting many electron problem into a non-interacting electrons moving in a mean field. So it means like you're trying to remove the interactions in the many electron problem and then trying to construct a mean field which is having this interactions lumped in, but you are trying to deal with a non-interacting electron system which is moving in a mean field. So the problem of finding the ground state electron density, which is what we're interested in, the lowest energy state of the system, and the electron density, which is nothing but probability of finding electrons at a given position, material point X. The problem of finding the ground state electron density of any electron system is actually equivalent to minimizing the energy function, which is shown in equation 1, subject to an orthonormality constraint. And if you look at the individual terms, which I'm going to use here, psi is psi1, psi2, psi ix, which is denoting the vector of single particle wave functions, because now I have an interacting electron system which is reduced and non-interacting electron system, and so every electron will have its associated fictitious single particle wave function, which are psi1, psi2, psi I of x, and the electron density rho of x, which is actually a non-interacting, which is actually an interacting electron density, because you are actually trying to reduce an interacting many electron problem into a non-interacting problem in a mean field. But because you have reduced the problem into a non-interacting electrons in mean field, this electron density is actually computed using single particle wave functions, which is basically given by this equation, which is here, which is summation of Fi mod psi I of x square, which is a relation between the electron density, which is a probability density of finding electron at a material point X, is written in terms of these single particle wave functions. And here R in this equation is something which is denoting the nuclear positions. For a given fixed positions of nuclear, this is what is the energy of the material system. So the kinetic energy here of non-interacting electrons, which is this Ts of psi, is basically is the kinetic energy of non-interacting electrons, because you've reduced the interacting electron system into a non-interacting electron system. So this is the so you know how to compute this kinetic energy of non-interacting electrons here. And the exchange correlation energy is something which lumps the effect of the interactions which you have neglected in reducing the interacting many electron problem into a non-interacting problem. And J is basically the classical electrostatic energy, which is again given as sum of three terms, which is basically the electron-electron interaction term, and the interaction between electron and the external potential, and the EZ, which is the nuclear-nuclear interaction term, which is a classical electrostatic repulsive energy. So now what we do here is, in order to actually deal with this non-local extended interactions which actually occur in this electrostatic interaction energy, because we want to work in real space, we actually try to introduce this a nuclear charge distribution B, which replaces this point charge. And we rewrite this particular double summation as again like a non-local extended interaction, just like we have in Hartree energy. And this involves self-energy, and hence we subtract out the self-energy. So the reason for doing this is we now can actually we can use the fact that 1 by mod of x minus x prime is a Green's function of Laplace operator. And we can actually write this electrostatic energy as a max-min problem over this auxiliary potential phi, which is arising because of the electron density in the nuclear charge distribution, and this Vi, the self-potential, which is arising because of this nuclear charge distribution B. And this electrostatic energy can be now written as a local form by introducing these auxiliary potentials. And hence the Kohn-Sham the Kohn-Sham problem, which I showed you before, the minimization problem, now it can be written as a min-max problem, where minimization is over the single particle wave function psi, and the max over the auxiliary electrostatic potential, which I introduced before, which is arising because of the electron density, the nuclear charge, and min-max over this Lagrangian L, which involves the kinetic energy of non-interacting electrons, the exchange correlation energy, and this particular min over Vi, which is over this self-potentials. Now, you actually, depending upon the kind of problem solving, is periodic or non-periodic, these spaces chi and y depends upon the space in which you're trying to solve the problem. Now, when you take the, this is, excuse me. Now, when you take the Euler-Lagrange equations, though in principle posing the problem as a local real space problem, it is nice, but from a computational standpoint, it is nice if we can actually write the Lagrange equations of this particular function and try to see what are the Gaussian differential equation which we have to actually solve in order to solve this density functional theory problem. So for that, we will, when we actually go ahead and write the Lagrange equations of the saddle point formulation, which I discussed before, we arrive at the following set of Gaussian differential equations. The key thing here is we have to solve a nonlinear eigenvalue problem. If you look at this as a nonlinear eigenvalue problem, because this particular eigen problem, which we are interested in solving for I is equal to 1 to n, we are interested in finding the lowest n eigen values and eigenstates, because we're interested in the ground state. And this particular operator, which is present, which is comprising of electron density, is again a function of these single particle wave functions. So which means the operator itself is a function of the eigenvectors, and hence you have to solve a nonlinear eigenvalue problem, which is for the n lowest eigenvalues, where n is dependent on the number of electrons in the system. So if you have more electrons in the system, you have to solve for many eigenfunctions in the particular problem. So which essentially tells you the complexity of the problem, because if my problem has some 100,000 electrons, I need to solve for, let's say, 100,000 wave functions, for instance, right? So this is the complexity in the problem. So we are not just interested in solving one or two lowest eigenvalues, but we are interested in solving many, many eigenvalues depending upon the size of the system you're considering, and not just solving an eigenvalue problem. This is a nonlinear eigenvalue problem, because you start with initial guess for electron density and then compute these operators Veffective and VNL, and then solve for eigenfunctions, lowest eigenfunctions, and again compute for electron density, and you do it in a self-consistent procedure. So that's why the self-consistent field iteration is the name which is given, which is essentially trying to solve the nonlinear eigenvalue problem starting from initial guess. So once you solve this, you compute the ground state electron density rho, which is what you require for computing ground state energy and other material properties of interest to you. So now, having seen the local real space formulation, they have introduced auxiliary potentials, self potentials, and the total electrostatic potentials. Now it is amenable for discretization, and we use finite-element discretization, and this particular community is not a new thing for this community, because this is an expert community in application of finite elements for many application areas. So as you know, the advantages of finite element basis, even in the context of density functional theory, is that adaptive spatial resolution, which can accommodate, and you can represent complex geometries if you want, and you can impose arbitrary boundary conditions, which is not possible today with the state of the art basis functions, which people use, at least the widely used basis functions. And then this, and because finite element bases are polynomials, you can expect systematic convergence with the basis sets. And there are different variants of these quantum mechanical calculations or DFT calculations, which involve smooth fields, which involves non-smooth fields. And because you are trying to use this finite element basis set, you can actually do both all electron and pseudo potential calculations, which is kind of trying to say all electron is something which you're trying to solve all the electrons in the system, and this appropriate single particle wave functions will be non-smooth, and the pseudo potential DFT calculations involve smooth wave functions. And because of the adaptive resolution which you are trying to incorporate in finite element basis, you can in fact solve both of these calculations in the same framework. And of course, the most important advantage is because these basis functions are local, it is amenable for parallel implementation, which means it is scalable on heavily parallel computing architectures. But the problem is, though finite elements have been routinely popular in many areas of science and engineering, this has not gained prominence in trying to solve these quantum mechanical equations. The main reason is, unlike other areas, here you are interested in computing material properties which have to be very, very accurate. So for this reason, a generic basis like finite element basis, which is a polynomial basis, has huge degree of freedom disadvantage because of the stringent accuracy requirements you have in computing the required material properties to the given accuracy. And further, because these basis functions are not orthogonal, it usually results in a generalized eigenvalue problem, which is more challenging to solve than a standard eigenvalue problem in terms of the numerical methodologies which you can employ. So, and if you look at the discretization, and here another thing which I want to emphasize here is that Because of these challenges, though initial proof of concept implementations of finite element basis sets in density functional theory dates back to 1980s, but there has no implementation which people can use for solving realistic problems and see that this method can compete with existing state-of-the-art methods and advantages in certain scenarios. And the kind of methods which actually I'm going to discuss actually have removed this restriction, have addressed the challenges, and then try to kind of make finite element basis competent with the existing state-of-the-art basis sets in regimes where you are looking at medium scale systems to large scale systems. So if you look at the discretization of this generalized eigenvalue problem, which actually, discretization of the Kohn-Sham DFT problem, which is a non-linear eigenvalue problem, which actually showed before, it results in a generalized eigenvalue problem. This is because, again, because of this overlap matrix, which is arising because of the non-orthogonality of the finite element basis functions. But this can be reduced to standard eigenvalue problem, which is using a simple trick, that is you do Chebyshev factorization of m, compute m power minus half, and you reformulate this. You can actually convert a standard eigenvalue problem, but this is only advantageous if you can compute m power minus half in an efficient manner. Yeah, people in other communities actually use this mass lumping approaches, which are ad hoc in terms of computing this mass matrix. But here, I will tell you how we actually compute this inverse m power minus half, because if you cannot compute m power minus half efficiently, the inversion, I mean, the computation or the solution of this transformed eigenvalue problem, which will become again expensive because m power minus half is need not have the sparsity of the finite element discretized matrix, and hence it becomes difficult computationally to actually deal with m power minus half if you do not have a computational cheap way of computing m power minus half. So and now, as I said, there are two key disadvantages, right? So the first thing can be addressed by using higher order finite element basis. And this is obvious because you're not getting accuracies with traditional linear and quadratic finite element basis, which people routinely use in fluid mechanics or solid mechanics community. But here we actually show that you actually require, in fact, you need to go to beyond FE order of 2, which means you actually have to look at FE orders, finite element interpolating polynomials to 6 and probably 7 in some cases as well. So here there is a benchmark study which you have done on a copper nanoparticle, which comprises of 55 atoms. And we are interested in solving the ground state energy, which is after computing the Kohn-Sham eigenvalue problem, compute electron density and compute energy. We are interested in computing the ground state energy to a required level of accuracy. Now, for that level of accuracy, if you actually tabulate the number of finite element degrees of freedom versus the finite element interpolating polynomial you require to solve this calculation, we see that as you keep increasing the FE order, you actually see a dramatic reduction in the degrees of freedom you require to solve the problem for a similar accuracy. And this is another benchmark case, which is showing in the case of a molybdenum periodic supercell with 53 atoms. So if you look at this particular case in both copper nanoparticle and this molybdenum supercell, which we actually observed in many systems as well, but here I'm putting two representative benchmarks, there is a dramatic reduction in the degrees of freedom. If you use FE order 2, you require 1,104 million degrees of freedom, whereas you just require 2.5 or 2.6 million degrees of freedom if you use a very higher order finite element. But does this reduce the reduction in the computational cost? Because as you keep increasing the finite element interpolating polynomial, your size of the discretized matrices, the bandwidth of the discretized matrices increases, and hence it brings in its own complexities in terms of computational cost and building these matrices, and also in the efficiency you would gain in iterative solvers by actually having higher conditioning, which you would probably lose out some computation efficiency if you actually go for higher order finite element interpolating polynomials. So the important question to ask is, does this reduction in degrees of freedom also translate to reduction in the computational cost? In fact, it indeed translates to reduction in computational cost. We get 1000x advantage by using higher order finite element basis, which is kind of unique only to this kind of problems, quantum mechanical modeling of materials. If you use finite element basis, you in fact require to go to 4th order or 6th order finite elements, and this is some old data data. Now we have done some new approach where we actually are floating atoms in the mesh without having to restrict the atoms on the finite element nodes. Then in that kind of approaches, we can actually in fact go to finite element interpolating polynomial to degree of 7 as well. So which is clearly demonstrating the advantage, not in terms of just reduction of degrees of freedom, but also in terms of computational gains which you incur in using higher order finite element bases. Now, next disadvantage is the generalized eigenvalue problem, which we have to solve, right? So here we do not use the conventional equispaced finite elements, which is traditionally used. But of course, I think now people are shifting towards these kind of spectral finite elements, which are actually Lagrange polynomials still constructed over the roots of derivatives of Legendre polynomials, as you can see here. And the advantage of these particular nodes are that if you actually use quadrature rules, which are coincident with these nodal locations, the mass matrix or the overlap matrix which you have, which is arising because of the non-orthogonality of the finite element basis functions, reduces to a diagonal matrix because of the nature of the property of this finite element shape functions, which is 1 at its node and 0 at other nodes, right? So if you use a quadrature rules which is coincident with the nodal locations, in fact, you can actually get a diagonal overlap matrix. But this is a reduced order quadrature rule in comparison to traditional Gauss quadrature rule. And hence we only use this Gauss-Lobato Legendre quadrature rules only for evaluating the integrals which are arising in this overlap matrix. But however, we actually use the traditional Gauss quadrature rule in basically computing this matrix H, which requires a higher accuracy in computing the integrals. Now, using higher order finite elements and then using these spectral finite elements where your nodal locations are at the roots of derivatives of Legendre polynomials. So in fact, you can actually the transformed standard eigenvalue problem becomes very easy to solve because your m power minus half is just the negative inverse square root of the diagonal entries of the overlap matrix. Now, having reduced the degrees of freedom and having transformed the generalized eigenvalue problem into a standard eigenvalue problem by using the spectral finite elements, next important question is how do you solve the eigenspace? Because here we're not interested in just one eigenvalue, one eigenvector, or 2 or 3, but we're interested in as many number of electrons are there in the material system. Okay, if you're considering spin, we are interested in half, and I should be more careful here. We're interested in half of the total number of electrons, but proportionately grows with the number of electrons in the system. So which means the number of eigenfunctions you are interested can be anywhere from 100 to 50,000. 200,000 eigenfunctions, lowest eigenfunctions to solve. So we require a very, very efficient eigenvalue solving strategies and also implementation of these strategies as well. So here we use a Chebyshev filtered subspace iteration procedure, which is an extension of power iterations to bunch of vectors, but except that you start with a bunch of vectors, but you basically try to filter out the unwanted eigenspace by using the action of the Chebyshev polynomials onto the starting space. So if you recall the power iteration actually is very popular where you are interested in finding the largest eigenvector. And if you take bunch of eigenvectors, in fact, if you orthogonalize at every step, you can show that those bunch of starting vectors converge the largest eigenvectors, which means eigenvectors correspond to largest eigenvalues of the associated matrix you are interested in. But however, there is a caveat here. The rate of convergence is dependent on how well the eigenvalues are separated. If you have eigenvalues which are not well separated, you have very, very slow convergence for these particular methods. So here, instead of hitting the matrix with these particular starting vectors, you instead hit with a Chebyshev polynomial of a matrix, because Chebyshev polynomials have a very nice fast growing property to the left of -1 in comparison to its growth between -1 to 1. So because in DFT, we are interested in the lowest end of the spectrum, which is to the left of A. We are interested in this wanted spectrum, and you have an unwanted spectrum, which is arising solely because of your discretization. This unwanted spectrum is mapped between -1 to 1, and the wanted spectrum is mapped to the left of -1. Because your Chebyshev polynomials grow very fast left of -1, you basically have you are basically exploiting the fact that you are dampening the unwanted spectrum and magnifying the wanted spectrum, which actually results in a very, very fast convergence of the eigenspace. And in fact, we did some studies in comparison to traditional eigensolvers like Langsdorff-based eigensolvers or Jacobi-Davidson-based approaches. So we actually can show that we are more than 20x faster than those traditional solvers if you use the Chebyshev filtered subspace iteration approaches for this kind of problems. And so summarizing all these things, you in fact have key important steps, which is compute. You start with a trial initial guess of wave functions, and you compute the discretized matrix, which is the finite element discretized matrix of the continuous partial differential equation eigenvalue problem which you want to solve. And then you basically compute the Chebyshev filtered vectors. That is, you compute the action of the Chebyshev polynomial onto the starting trial space of vectors. And then you orthonormalize these Chebyshev filtered bases. And then you have this Rayleigh-Ridge procedure, which is standard in any iterative orthogonal projection kind of techniques for solving eigenvalue problems, where you compute the projected Hamiltonian into the Chebyshev filtered space, which is you're projecting the finite element discretized Hamiltonian H tilde into the projected space, into Chebyshev filtered space, which this projected Hamiltonian will be a smaller Hamiltonian, and you diagonalize the projected space, and then you do a subspace rotation to recover the eigenvectors in the original space, and then you compute the electron density using these rotated eigenvectors. So this is usually called subspace rotation in the numerical in algebra community. So these three steps basically are repeated till your electron density converges in the self-consistent field iteration. So the most computationally expensive parts of these particular procedure is the Chebyshev filtering, orthonormalization, and the Rayleigh procedures. So now, so before getting into the implementation aspects of these particular methods, I'm going to comment upon the accuracies, and this is just a slide which compares the ground state energies and ground energy accuracies with the state-of-the-art codes out there. You take a problem and solve using your finite element based approach, which I just discussed, and solve the same problem with the existing codes out there. Here we used a quantum espresso, which uses sines and cosines Fourier basis as a basis sets, and we kind of try to compare the accuracies of both the calculations in terms of the ground state energies, because that's important when you have a new method. You need to benchmark against the existing state-of-the-art codes out there. And for various benchmark systems, we did the studies and we find the accuracies of our energies and energies computed using plane wave codes matched to a very good accuracy. Okay, so now having seen how did we reduce the degrees of freedom and how did we employ spectral finite elements to actually take advantage of the transformed standard eigenvalue problem, and then use of Chebyshev filtered approach, which combines with the advantage of having a standard eigenvalue problem. We have seen that we have addressed some of the key issues which we have mentioned before. But this is not enough, because once you have, if you want to squeeze the juice out of your formulation, it's important to implement efficiently, which can take advantage of today's heterogeneous computing architecture. So I would want to throw some light on that very briefly. So as we are trying to solve for the largest eigenvectors, which means eigenvalue, largest eigenvectors in the sense eigenvectors correspond to largest eigenvalues. We are interested in computing the smallest, lowest eigenvectors, which means the eigenvectors correspond to lowest eigenvalues. But because we are magnifying the spectrum, it so happens that it becomes the largest eigenvectors for the transformed Chebyshev filtered polynomial of the discretized matrix H. But in principle, we are interested in computing the smallest eigenvectors and eigenvalues of our discretized Kohn-Sham finite element matrix. Now, the key kernel which actually goes in employing a Chebyshev filtering procedure is this H time X, this is just enough to recursively build the Chebyshev polynomial so that you can construct efficiently the action of Chebyshev polynomial on the starting vector space, okay, starting the space of trial space of vectors which you're starting with. So here the H is the, and of course, subsequently the other multiplications which actually happen during the course of the recursive iterations. So if you look at this particular key kernel, which is essentially matrix vector multiplication. So H is a sparse matrix, which is of the size m cross n, where m is the finite element nodes in the mesh, and n here is number of eigenvectors you're interested in solving. So in principle, you can actually assemble this global matrix, and then you can accomplish this parallel sparse H matrix times a dense wave function matrix, because X is basically a trial guess of wave functions, right? So when you have this trial guess of wave functions, it's a dense matrix. There's no sparsity requirement there. So this is computationally expensive to actually accomplish this. So what we do is we actually compute the element level or the cell level finite element discretized matrices. And I'm calling this finite element discretized Hamiltonians. In the mechanics community, they're called finite element Kohn-Sham. So finite element stiffness matrices. So here it's a Kohn-Sham Hamiltonian at the cell level. And we construct the Kohn-Sham Hamiltonian at the cell level and extract the Kohn-Sham wave functions X at the cell level, multiply this at the cell level, and then assemble to form the global vector. So here, if you see, there is this particular color coding, which each color represents a given processor. And you actually have a lot of wave functions N, which you want to compute, but probably there are some memory requirements we have to keep in mind. So we actually deal with a block size BF. We don't deal with all N wave functions in one go. So we extract a BF block size, and then you convert this particular wave function vectors, which is the global level, to a cell level vectors, which essentially means you are trying to compute this XPCI. So you already have you don't assemble the big matrix, but you compute only the cell level stiffness matrix. So when you actually compute the cell level stiffness matrix or the Hamiltonian matrix, and you can perform these particular operations in parallel, because each cell need not talk to other cell. So each processor can do its own operations, and each cell in each processor can be independent of each operations, and it can massively exploit the parallel. If you are using a CPUs, it can exploit the threads, or if you're using GPUs, you can actually exploit the GPU processing units. So then you can use some efficient libraries called shaded batch gems, and you can actually do this with less memory access costs. And finally, you compute the product vectors at the cell level, and then you assemble it to form the global vectors. Now, once you finish this particular vector is done on each processor, but you also have to assemble across each processor. So now that is just a nearest neighbor communication, because finite elements are just localized in real space. But because you are actually doing a nearest to nearest neighbor communication, where you need not communicate with not all processors, but only few processors sharing, only the processor sharing that node, which will be few in number because basis functions are localized in nature. And because of that, we can afford to actually reduce the communication cost by using single precision communication at the processor boundaries. So we actually do an FP32, which is a single precision communication at the processor boundary, which actually reduces the data moment costs further. So here is just some example where you actually can find how the computational, how the throughput performance. So this is called a throughput performance on the y-axis. So what is throughput performance trying to say is, so how many useful floating point operations I'm trying to do, which means how many floating point operations per byte of memory access I'm trying to do. In a way, it's a measure of arithmetic intensity. So if I'm actually having a good throughput performance, which means I'm not wasting any floating point operations, I'm doing a lot of floating point operations per byte of memory access cost. So a higher throughput actually means a higher performance gains in your computational time and your implementation, which is trying to efficiently use the architecture in which you're running the code. And so we just see that we actually can get up to 50% of the throughput performance, which is a significant thing, which means you're efficiently trying to hit the 50% of the total available peak performance on your machine. If there is no a wastage of your floating point operations, which means if there is no data access cost, in fact, you will achieve 100% peak performance. But because there is data access and everything, you are able to, your observed peak performance will reduce, or your observed performance, sustained performance will reduce, but we have still achieved 50% of the theoretical, 50% of the peak, which is theoretical. So, and again, if you see a comparison of the improvement in the sustained performance, where you actually kind of can introduce some efficient HPC implementation strategies, where you can actually do some communication while the compute is happening, and those kinds of efficient implementations. In comparison to the baseline, we actually can improve the sustained performance, which was 21% to 43%. So this kind of clearly shows that how much gains you can incur, in fact, how much gains you can achieve by a properly designed choice of the algorithm in the implementation and its implementation. So here, then we actually talk about, then the next most important computational step is orthogonalization, which is essentially computing this overlap matrices. And these overlap matrices are just some kind of X transpose X kind of matrices, which are parallel and distributed across all the processors. And this is an computationally expensive operation when you are number of atoms or number of electrons in the system is more, which is an order mn square computational cost. And again, we try to exploit some data moment friendly algorithms where we actually identify that in your subspace iteration procedure, you are essentially interested in converging to the Eigen-space. And as you're converging to the Eigen-space, this overlap matrix associated with the Chebyshev filtered vectors actually becomes identity, because your eigenvectors of a symmetric matrix are orthogonal, and here our finite-element discretized matrix is symmetric. In this, I'm assuming real data structure here, and you have orthogonal eigenvectors, and hence your overlap matrix is identity. So we can exploit this. So in the initial SCF iterations, you will not have identity, but as the SCF progresses, where you are actually converging to the accurate self-consistent Eigen-space, you can actually take advantage of this and compute only diagonal entries in double precision and off-diagonal entries in single precision. And when you're trying to do this, you can actually get a lot of computational advantage, because when you're computing something in single precision, you're reducing the compute, and the associated communication which involves in computing this overlap matrix will also reduce, because you are actually doing this communication in single precision essentially. So this again improved the computational efficiency of our implementation. And again, we actually made sure that we have nice overlaps between computes and communication, so that when your compute is happening, you can communicate on the side. So we have different blocks, and when each block is doing this compute, other block can do its data movement, and thus that way things are hidden behind compute, or things are hidden behind communication, depending upon which our cost is higher. So these kind of HPC-centric implementations, again, improved our performance substantially from the baseline, which is 30.9%, for example, in the overlap matrix computation, to 77.6% throughput, which means we're able to reach 70% of the total peak in kind of implementing these mixed precision strategies and in trying to devise these kind of asynchronous compute communication programming paradigms. And similar thing, we also did it in the subspace projection, the real projection, where you have to compute a projected Hamiltonian. And we use a similar strategy where we can compute diagonal entries in double precision and off diagonal in single precision. And again, we see that we have got a significant performance boost from the baseline to the actual implementation, which involved mixed precision and compute and asynchronous programming paradigms. So when we have these kind of techniques, we actually have to make sure that we measure the accuracy and the robustness. And we actually did some benchmarks, and we found that we did not incur much error in the properties we are trying to compute, because as we are trying to intelligently come up with these mixed precision algorithms, where we know that things are becoming anyway reducing to diagonal, and hence off diagonal entries are becoming smaller, and hence we compute them in lower precision will not incur any error in the final energies and forces we're looking at. And putting all these together, I would just want to maybe spend 5 minutes, because I think I only have 5 more minutes to wrap up my talk. So we actually did comparisons with the state-of-the-art codes, and we find that as you keep increasing system size, we are actually much significantly faster than the conventional state-of-the-art codes. And we did it on various systems here. And we also studied the scalability, where we actually went up to 6,000 GPUs, and we saw that we reached up to 96% efficiency until this regime, and we actually are up to 40% efficiency when we keep on scaling, which is a very good scaling efficiency, because we have very less degrees of freedom per GPU on the GPUs. And CPUs also, we actually significantly scale. So we are almost at 60%, 70% efficiency with just having 500 degrees of freedom per processor. And then we also did a weak scaling, which actually highlights the fact that you are asymptotic, you are actually delaying the asymptotic computation complexity, which otherwise would have scaled cubically with number of atoms. Now you're delaying the asymptotic computation complexity because of the reduction in the prefactor you have in the implementation procedures we have actually developed. And this is basically comparison of the minimum wall times. That is, you take a state-of-the-art code and keep on increasing GPUs or CPUs and wait till you reduce the time and where the time flattens off, and take that as your minimum wall time, and do that in our implementation with finite elements, and do that with an implementation with an existing code out there, and compare the difference with time. That's called a minimum wall time comparison. And we see that even at small systems, we are significantly faster than plain wave-based code out there. And as you keep increasing the system size, this factor actually drastically, we have a greater speed ups, almost like you can say 20x speedups we actually have in comparison to, not 20x, sorry, roughly 10x speedups we have in comparison to a minimum wall time which you obtain with the state-of-the-art codes out there. Yeah, and this, we actually also demonstrated this particular methodologies on 100,000 electron system, and we could actually solve this, and we achieved 50% peak for the full problem, which is what allowed us to get a nomination for this ACM Gordon Prize finalist in 2019. And we also have an open source code which actually implements all these things and for users to use out there who are interested in quantum modeling of materials. We have released a purely CPU code in 2019 and GPU code just last month, which has all these advances. And in our group at IISc, we are also working on further accelerating the computational efficiency of some of these matrix multi-vector products which arise in Poisson problems, which we actually need to solve in a DFT calculation, where without trying to build the matrix here, so far we're trying to build the matrix, cell level matrix, and compute matrix vector multiplications. But instead, without building the matrix, we are trying to actually do on the fly matrix free computations. But this matrix free computations, which already exist in libraries like DEAL2, does not allow for multi-vector products. So we are trying to build strategies which can actually allow us to actually do on the fly matrix multi-vector products, which the initial results show that they're actually faster than the DEAL2's matrix free implementations as well for a single vector for the Poisson problem. And we are also trying to incorporate various levels of sophistications in density functional theory, which actually allows us to handle more wide variety of materials. For example, in the case of energy storage materials, the exchange correlation functional we have takes a different form. And in order to improve the computational efficiency and reduce degrees of freedom, there are sophisticated pseudo potentials which will employ, which changes the complete governing equations. And then we have to develop these strategies again to solve those problems as well. And we are trying to collaborate with application experts to leverage these computational efficient techniques to actually solve some complex material science problems which cannot be addressed in the case of energy storage materials today. And there are some other works which are going on in trying to accelerate the subspace diagonalization after release projection by using polynomial expansion approaches, and then trying to, as I said, improve the level of sophistication we have in density functional theory to solve a wide variety of material properties used for a wide variety of applications. And our application problems today are basically in energy storage materials and in mechanical properties of materials to understand failure mechanisms in metallic classes. So with this, I would like to thank my current and past collaborators, which made this work feasible. And I also acknowledge the current funding agencies, IISc grant and SCRB startup grant, and NSM R&D for exascale in India. And we have collaborators across the world, which help us in many aspects of our work in trying to find useful applications for what we are trying to do. And these are some of the publications which you actually can also refer in my website. And thank you so much for your attention.